the MPPT technique. So till yesterday we just saw the simulation part. Is it? We just saw how to simulate the input, like how to simulate the overall system and how to see the output. But with simulation, nothing is going to happen. Any system, you have to bring it into real time. Then only there is some fruitful output you get. So I'll be just giving you an insight how to implement it in hardware. So we have done the whole system which I explained you yesterday in our laboratory. So the students, like the participants here at the NITA center, tomorrow afternoon. Okay, so today afternoon also I think there'll be some other lecture. So tomorrow afternoon when you're free, we will be taking you to the lab and we'll be showing you the all system. Those who are here. For others, I'll just explain the procedure. With DSpace we have connected, that is a DSP processor. So I'll be just explaining what is the procedure to follow in order to implement this MPPT technique in hardware. Okay. And the other the problem here is DSP processor, that is the whole DSpace kit cannot be brought here. It is an overall setup with all, you require a separate CPU with PCI slot and all those things. So that system we couldn't bring it here. So what I thought is, just to make you understand the concept of how to acquire any signal from the outside world into a computer and how to bring the signal out of this computer. Okay, using DAC card, that I'll be just showing you using a microcontroller, which is an Arduino controller, which I have brought here today. So with that, you will understand, okay, how to acquire the signal, how to bring it out using MATLAB. I'll be just showing you using MATLAB. So this Arduino can also be used for this MPPT technique. Okay, so that will be covered in today's lecture. So first of all, let us go. Yesterday, we were just seeing the simulation part, and now we will just see the hardware, which I told you is the thing which you can see on the screen. We have the system in our laboratory. So you can see here a 37 watts Vikram solar module. So yesterday I showed you that Vikram solar module, how to include in the MATLAB environment. You have to take the data sheet, go to mask and mask the parameters, put the initialization, you have to put all the parameters. So that Vikram solar module is shown here. So first, in order to conduct the experiment, we just had a small performance test. We just thought, let us keep the solar panel in the sunlight and see how it is performing, what is the efficiency. As I already told you yesterday, this system was around 13. It gave us an efficiency of 13%. But I told there are PV panels with 46% efficiency also. So first of all, we have to see what is the performance of our PV panel which we have. So for that, we just did a small experimentation. For that, first we took a solar power meter. So you can see the meter here. It is a irradiation meter. Okay, it gives you the values in BTU or otherwise watts per meter squared. So we just kept the solar power meter at different instances, and we saw the irradiation. So if you take a small panel, if you keep at one corner, it will give you one irradiation. At the other corner, it will give you other. It is not uniform. Okay, that is there. So what usually when we do the experimentation, what we do, we take an average. We keep it at different places and we just say around 10 values we have taken. This 10 values average we will take, and that will be our irradiation at particular instant. So for this we had, I can just show you the solar module analyzer here. At the left side, you can see here a solar module analyzer. So this module analyzer gives you, we have to just enter what is the irradiation of this panel inside that. Okay, and the temperature also. So here you can see under this panel, we kept here a thermometer. Okay, or you can use some LM35 or some sensor also you can use. So what we did, we just measured what is the temperature under this panel. We kept a thermometer and we measured it. And same way the irradiation was measured and we entered it inside this solar module analyzer. So I can just show you the picture of the solar module analyzer. And what happens is once you enter, automatically it will give you the characteristics. So you can see here the characteristics. Automatically it will plot you the characteristics at that particular instant and it will give you the efficiency. So you can see here it is around 9.946% at that instant. Okay, so we took average, we took many readings, like around 30 or 40 readings continuously we took, and we found the average of the efficiency. So we got around, again, according to the data sheet, it should be around 12 to 13%. So that efficiency we got after doing the experimentation inside the laboratory, outside the laboratory, in the field. So here what we did, first of all, we did the experimentation panel in between like 0 degrees when it was flat. After that, what we did, we just tilted the panel to 45 degrees. So here you have a protractor where you can just see what angle it is tilted. So we then tilted the thing around 45 degrees, and again we did the same experimentation and found what is the efficiency. After doing it outside, because say when we want to do the MPPT, we have to see that all the algorithms, P&O, incremental, GA, PSO, whichever algorithm you're doing, they have to be done at the same condition. If it is slanting, then irradiation is the same irradiation temperature, then only we can compare. Okay, when you want to compare 2 or 3 parameters, if they are at different irradiations or different temperature, there is no use of comparing it. So that's why this outside, when you do it in the field, it is very difficult. There will be cloudy, there will be some, suddenly sunlight will not be, suddenly it will come. So it was very difficult to do the experimentation outside. So we found it outside what is the efficiency coming, and again we did the same experimentation inside the laboratory also. Same thing. With the solar power meter, we just found what are the different, so we found the irradiation, because at different instance, we kept around 10 places here and 10 places, and we took the average. So that average will give you the total irradiation falling in this. Here, halogen lamp, inside halogen lamps was used, that the lamp which you use should have a range like between UV rays and the ultraviolet, ultraviolet and the ultraviolet and visible region, ultraviolet and what is it, ultraviolet and one more range. IR is infrared, sorry, yeah, infrared, ultraviolet and visible. In that region, if you have, that will be equivalent to the sunlight. So the light which you're using should have the IR, the ultraviolet UV, as well as in the visible. In that region, then it will act like the solar radiation itself. So maintaining it, you have here adjustment. I can just show you here. Here, see, we removed that light. Okay, and in this case, we have the light, and here they have the adjustment. A screw is there to pull it up, pull it down. You can tilt it, tilt the panel also. You have some option that I can show it in the lab. We have it. Okay, so that you can do it. All these adjustments, how. So here in the lab also, we for a particular irradiation we have set, and we have done all the experimentation. So here, this is the solar module analyzer. So, and this was the result. You can see here inside the laboratory at 0 degrees we did and 45 degrees we did. The irradiation inside couldn't be increased much because there is a limitation. We put both the halogens at maximum light. Their intensity of the light can also be shared, but we did the maximum because it depends on the room light also. Say if it is we are doing in the afternoon, there is more room light with the halogen lamp, it will give more irradiation. But when we did, we got only maximum 450 watts per meter squared. So with that, both lab condition and temperature was around 30 degrees. So we did this 0 degrees tilt and 45 degrees tilt we did, and the efficiency came out to be. This is with the solar module analyzer. It will automatically give you. You need not do anything. It was 1.446% in the first case, and for 45 degrees, 2.11 was the thing. So we did it many times. It was not a single time. It was an average. Average value was taken here. So similarly, outdoor also we did. And outdoor you can see 0 degrees and 45. It gave me an efficiency of 11.25 and 7.64 was for 0 degrees. So this shows that when the panel, as yesterday also I told you, according to the latitude and longitude of your place, if you keep at a particular angle, that will surely give you a better efficiency. So in all these cases, you can see when it was 0 degrees inside the lab, it gave the minimum efficiency. But our main aim is not to measure the efficiency. Our thing is if 1.44 is the efficiency at the input of the solar panel, that has to go to the output also. We are not concerned about the efficiency of the original panel. So panel will have an efficiency. Our main aim is to that conversion efficiency. Take this full power to the output, our load. Okay, so you can see here inside the lab, if you do, the efficiency will be less, but our main aim is not to increase the efficiency inside the lab or something. Our main aim is when we go and keep it outside, it has to give better efficiency with P-endo technique or any maximum power point tracking technique. So you understood inside the lab, it may not give good a result. When you go and keep it in the real time, it will surely give you real result. So that is understood here. Okay. But as I already told you, we can't go and do it outside because all these equipments should also be taken out and all these problems are there. So what we did the whole experiment inside our laboratory only. So this was the whole setup. And the one more problem was like tilting this inside the laboratory was also a little difficult for us because we required to take the irradiation also inside the computer. So in this experimentation, you can see here, this is the D space and there are 4 wires going. 1, 2, 3 and 4 wires are there. This 4 wires is nothing but we took 4 parameters inside. One is our temperature, irradiation, voltage and current when we did experimentation. So irradiation, what we did, we made our irradiation meter here. You can see here, we kept a small panel here. Okay, for experimentation, we were using this panel. We just covered the other panel fully. Okay, and we just took only 2 panels are there. We can connect it in series of panels. We took only 1 panel at a time. What we did is here you have a knob where you can adjust the lamp intensity. So we set this intensity and this intensity same. Okay, it was same light falling on both the panels. So here we kept a small panel, okay, of 1 meter square, like small panel was there, and in that we made this light fall, and again the same light was falling here also in this side. And now with this solar module analyzer, this is the irradiation meter. We just kept the irradiation meter at different instances. We took the average irradiation falling on it. Okay, so we now know, say around, say just keep 800 watts per meter squared is the average irradiation falling here. So that 800 irradiation is falling here also. So what we found is, what is the output voltage of this panel for that 800? So we calibrated it. Now 800, say some 8 volts is falling. Okay, we took that inside the computer and we multiplied with 100 and we told the computer that the irradiation is 800 watts per meter squared. Can you understand? So we have to calibrate it. So we made our own sensor there, irradiation sensor, because we want everything in terms of voltage. Then we use a LM35, so that for measuring the temperature. So, this was the different irradiation sensor. This was the irradiation sensor used. Here you can see one was for voltage, current measurement. Yesterday I showed you the diagram. Do you remember the solar panel, the DC to DC converter, and the load was there? You had a potential divider there where I took the voltage, and in the reverse path there was a resistor which I took inside. I think all of you remember the diagram. So same thing, that potential dividers are here. Okay, so this was directly the voltage and current measurement which was given to the D space. If you want, I can just show you the diagram which I showed you yesterday. So this was the thing. Okay, so in this system you can see here, you have a PV panel, and this 1 and 2 is the potential divider where you took the across 2, what is the voltage drop you took inside the D space. 3, that is the current sensor, you took it inside. Here I have shown this 4. This 4 is the irradiation meter. Okay, and temperature also if you want to take inside, or here our panel. Yeah, behind the module, they have given a small knob. So you can just go and insert your sensor there. So automatically it will measure. So here they have given the sensor, and this one is the temperature reading. This is not much clear. Temperature reading comes here also. If you want, you can just see that. And because all these experiments within seconds you're doing it, so you can measure, you can see that value and enter inside your computer. You can do that also. Okay, so otherwise, irradiation also, if irradiation meter is not there, what you can do is you can measure the value and give it as input it. So, but we wanted to do it real time. We want to acquire it and calibrate it properly and do it. So this you can do it. Okay. So here what we did, we have given all these parameters to the D space. So that's what I was telling. Instead of using this D space here, this is a DSP processor, you can use microcontrollers also. Okay. So one of the microcontroller, I'll be just showing you how to acquire data and give it inside. So let us finish this theory part, then we will go into that. So next, this is the D space. Okay, this was the D space board. This is 1104 D space 1104 model, and it has here 8 You can see here it has 8 analog to digital converters. Okay, 8 analog to digital converters. So here 1, 2, 3, and 4 you can see these are individual terminals which you can give, and sorry, these 5, 6, 7, and 8 are individual terminals, and this 1, 2, 3, 4 are muxed. Okay, so I'll tell you what is muxed also. At the same time, you can give many signals. That is, 4 signals can pass through the same channel. When we see the block, block like in the front, when I show some more slides, those blocks will come, so you will understand still clear. Apart from that, you have digital to analog converters also. When you want to take outputs, you can convert the digital value into analog, and you can take. You have digital input-output terminals. You have PWM terminals. You can generate PWMs. If you want, RS-232 ports are also given. When you are doing robotic application, you can use these ports. Okay, so these are different ports there, and these are some of the indications, just which are the things on off that you can see here. And this panel, which you can see here, this is the whole panel. It doesn't have any controller inside. Okay, these are just input output ports. After that, you can see here a black wire, big mota black wire is there. So this wire is connected to the end. Here you can see a silver end. You can see here a silver port here. So this port is connected to this PCI slot. Okay, so that will be connected to this here. Here you like this side also you have a, here you have a terminal. Okay, here there will be a terminal. You will be connecting this black wire to that terminal, and this is the controller. This is the DSP controller. Okay, this whole controller, you will be connecting it to your CPU through this PCI slot. Okay, your CPU should have the PCI slot. Okay, all the CPUs will not have it. You should choose a CPU which has PCI slot. You can insert this controller. So this is a DSP controller that is being inserted, and the other end is this one. This you can see, but this will be inside your computer. You will not be able to see. This is inside your CPU. You will not be able to see. We can see this terminal, and or you can connect like the probes what you use in your CRO. Same way, the probes you can connect all these probes here, all these terminals. So you can give my, if I want to give 4 inputs, I will be giving through my ADC analog to digital conversion channel 1, 2, 3, 4. Anyway, you can just give 4 inputs. Okay. So I'll be just showing you one by one how the hardware also I've taken the videos. It will be clear. So here you can see the characteristics of this DS1104. So this DSpace also different processors are there. They have now ACE box. Okay, so the ACE box of DSpace, they have FPGA inside with more number of input output ports, around 64 ports or something they have. So depending on your application, you can choose which DSpace you want. Okay, you want FPGA based with high end processing, you can go for ACE box. And DS1103, that is also a higher end of the 1104. You have 1102. So many models are there with them. According to our application, you have to choose it. So in this model, if you see, it has 2 processors. One is the master processor, which is seen here, MPC8240 processor, which is a 64-bit floating point processor, and its speed is 250 megahertz. So 250, you can just imagine, very high switching frequency. Power electronics application, this is very good. 250 megahertz CPU is there. And apart from that, again, you have one more processor here, that is the slave DSP subsystem is there, which is an TI, that is Texas Instrument TMS 320F240 DSP board. And that like its clock frequency is 20 megahertz. You can see 20 megahertz, and it's 16-bit processor. Okay, so this you can just here when we do it, we don't want to know about what is the internal detail, because we are just giving the analog input and it goes into the computer. But if you want to do more processing, then you can go inside and like change it according to your requirement. Okay, so this is the processor available. And in MATLAB, say when you, I'll just show you the video so you'll understand. DSpace people will come and install everything for you. You need not do any installation. And when you, and I was just telling you about the controllers. Is it we were telling about the DSpace processor. I was just showing you this. like a DSP process is just like the microcontroller. Okay, what will microcontroller do? When you give, so you have some sensors, you can acquire the signal and give it to the ports of the microcontroller. Microcontroller will do some processing and it will give you some output at some other ports. Okay, same way here also this DSP processor also, it is a DSP processor. Just like that, it has also input-output ports. You just give the input and you just take the output. Okay, and you can flash your program into it. Once you flash the program inside it, it will run dedicated. Okay, so next is when you go to the MATLAB environment, say we have seen these, you can see here all the ports here. These ports, MATLAB should understand that the signal is coming from this first channel. It is coming from the second channel. How will MATLAB understand from which channel the signal is coming? For that, you have this RTI block in MATLAB. So when you go to the command prompt in MATLAB, okay, and just put RTI, real-time interface, automatically this window will open. And in this window, you have different things like master PCC, slave DSP, F240, task library, extra. All the libraries are there. You want to use your master master processor, you can go and take the elements from this. If you want from the slave, you can take from this. Okay. So when you click on this master PCC was the first processor which I showed with 250 megahertz. Okay, 240 megahertz frequency. So all these blocks are there. So all these analog to digital converters, multiplex ADCs are there, DACs are there, all the master bits, bit out, when you want to take some bit outside, serial communication, all these blocks are there. What you have to do is just drag this and put it inside your Simulink environment. Whichever port you want, you have to drag and put it inside your Simulink environment. That also I'll be showing you. So here, see, when you drag this element and put it in the Simulink environment, you can see here ADC. So this will be dragged and put, and this, when you double click on it, this window will open. Okay, there you can just go and choose which channel you have connected your current or voltage, things, say 5th channel, 6th channel, like that. Okay, similarly, you can see here for the MUXed. So this is what I said. In MUXed, you have an option to tick number of channels. The last case, only one you can choose. That was not MUXed. So here, at the same time, 4 signals can be passed inside. Okay, is it clear? So this is a MUXed ADC. And then you have PWM channels here. Okay, so in PWM channel till 5 megahertz. Here PWM, if you see, this is the slave. This PWM is using the slave DSP, and here you can see till 5 megahertz frequency you can generate firing pulse. So here around 8 kilohertz, 80 kilohertz frequency. Because when I think you remember when we designed the buck converter, I gave that as 80 kilohertz. You remember the current ripple was 10% and the 80 kilohertz. Accordingly, we found what is the LC. So the frequency at which we are firing the PWM, we are generating the PWM is 80 kilohertz. That is what you can see here. Okay. So now what we did, I think all of you remember this P&O block. This P&O block yesterday I showed you in simulation. So with this P&O block yesterday we had the PV panel connected, we had the load, everything. So when you want to implement in real time, only the control circuit you take, all the power circuit you have to remove. You have to just remember this. Okay? Because power circuit cannot be embedded in a controller. Okay, power circuit is a very high voltage thing. How will you embed it? So only the control circuit. So what was the control circuit in the circuit which I showed you yesterday? Only the P&O. Do you remember the MATLAB model which I showed you yesterday? There was a PV, the input was irradiation and temperature. Then we had a buck converter, then the load, and then the buck converter switch was fired using a PWM with this P&O. So in this whole circuit, the P&O is the control circuit which is generating my firing pulse. Only that can be burnt in the controller. So I've just taken my P&O. In this P&O place, I can have incremental conductance INC, I can have my artificial neural network, I can have the ANFIS, I can have GA, anything here. So now I am just taking my DSpace input here. I am giving it to my P&O, okay, voltage. Then I am just measuring, I am using my MUX block, even ADC or another channel also, 6th channel also, if you want, you can use. I am using the MUX here and I'm giving the current inside, okay. And after that, the output output of this is nothing but my duty cycle. So you can see here the duty cycle is coming as output. I'm saturating it. I just want my duty cycle to vary between 0.4 and 0.9. If a value more than that comes, I'm just saturating it to 0.9. Okay, because firing, I told you this firing angle also has a limit. Okay, so that's why we just limited between 0.4 and 0.9 saturation was given here. And this is the PWM channel. Okay, so at a time, around 8 PWMs can be generated. One PWM channel will generate 2 PWMs. Okay, and if you want to using a NOT gate, say 1 PWM is coming, with a NOT gate, you can just give the opposite thyristor. So you can just 8, you can generate. I'm not going to generate in the other, so I've just put a 0 with, as I told you, 2 signals should go into 1. Okay, so if you connect it directly 0, that will give you an error. So here I put a mux here and I generated 2 signals here, and these 2 signals are made 0. This PWM channel is made 0. Similarly here, these 2 channels are made 0, and this signal is going inside. Okay, so with a delay, like first one duty cycle is going, then with a delay the other duty cycle will go. So 2 signals has to be given to it. So this is the overall structure of your PWM. Okay, similarly that P and O I'm just changing, and I'm giving a neural network here. If you have taken the data and you have trained a neural network, you can have a neural network. If you want, you can have ANFIS, GA, whatever you want. After that, see, now we have to find what is the efficiency of my system. Okay, say I have done MPPT and I am getting an output. So can you say that output is the best output? How will you find the efficiency? For that, you have a formula. The efficiency of this MPPT is, you can see here the efficiency of the MPPT is the power output which you got with MPPT divided by what should be the maximum power. Okay, what should be the maximum power output for a particular irradiation and temperature. So you just take the solar panel, you see what is it. That's why I just kept the irradiation meter and so the temperature meter there. Okay, I took that input in order to just measure the efficiency. But when I'm going to give it in the real time, that is not required. I can remove this irradiation. That just to find the efficiency of the system, I've used 2 sensors extra. Okay, so what I'll do here now, I have to find what is my MPPT efficiency. That is what efficiency, power, voltage and current will be the output of the MPPT. There I can measure and multiply. You will get the MPPT output. Now I have to see what is the panel output. What output should come. Okay, because that say depending on the irradiation falling on it and what is the temperature of the panel, what should be the maximum power. For that, many prediction models are there. So maximum power prediction model. So the maximum power depends on 3 terms. You can see here, it depends on 3 terms. It depends on the fill factor, okay, which is given by this formula here. This is the fill factor. Okay, then open circuit voltage. This is the open circuit voltage, and it depends on the short circuit current. So it depends on 3 parameters here. And all the things like G is nothing but the irradiation. G naught is the irradiation under normal, like standard test condition. Okay, so you have to find all these values. T naught is under test condition. That is, you know that for a standard PV panel, it is 1000 watts per meter squared is the standard irradiation under test condition, and 25 degrees C is the temperature under standard test condition. So those are the standard condition, and you will be measuring at a particular instant what is the G and T value. So you, and the other parameters also, all the parameters you have to measure and put inside it. So that formula is only given here. Short circuit current is given by like this, open circuit voltage and fill factor. So put all these parameters, and for this what we did, again we made a MATLAB model. Okay, so MATLAB model, I will show you the MATLAB model also. So this was the maximum power output prediction model. Okay, so for the here G I am giving the temperature, and this will give me my the outputs, the maximum. Say this was the for the fill factor. Okay, the MATLAB model was, I'll show you the MATLAB itself. You will understand it. So simply I'm showing this is for the fill factor. The upper one was for open circuit voltage, and the lower one was for short circuit current. Okay, so all the values are there. You have to just make the model. And when I found the output, you can see here my irradiation. This was my irradiation. First I had 1000 watts per meter squared. Then suddenly I changed to my some 300 or something. Then again I increased and 1000 watts per meter squared. Okay, this was the irradiation. So you can see that irradiation, I have taken the scale this side in MATLAB. Okay, 1000, because this side the scale is 40. If I put 1000, then all the 40 values will be very small. It will not be visible. So for visibility, I have taken only the irradiation on the right side, and all the other parameters are here. So you can see here, this model was maximum power. Say when it was 1000 watts per meter squared, around 37 watts it is tracking. My panel is having 37 watts, is it? So my prediction model is good. And what I did after that, you can see here, when the radiation less, it is around here 8, like when it was 300 watts per meter squared, my power was very less. Then again I increased it. So this is tracking my water according to the irradiation and temperature input. It is giving me my correct Pmax output. Okay, so this model was chosen from IEEE paper itself. So you require, I have taken a IEEE paper, I have just seen what they have done, same thing model we have done it. And now what you have to do, in real time, you have to, when you're doing it in hardware, you have to just use this model. You will be using this model, only this model. I showed you 4 inputs to my DSpace. One of the input, I'll give temperature to real-time temperature using DSpace. Irradiation also, I showed you irradiation meter where we measured it. That input you will be giving here. So it will automatically, this Pmax, I can measure, which is the power output, maximum power output. Okay, real time also, take the irradiation falling at that time, take the temperature, and this will give me what is my Pmax. Okay, so this is what we are doing. Then we will be using Excel or something. You can just take down all the data and find the efficiency. So this is how we find the efficiency of a system. So once you finish that, say this was a real-time experimentation, what we did, we just turned on the light in our laboratory, just turn on the light. So suddenly there is an increase. And inside the laboratory, you know, much light will not come. So there was around, say, when we did it in real time, during that time, what was the thing? It was irradiation was very less, around or something only was there. This red one is the irradiation. You can see here on the right side. So the irradiation was less, and Pmax calculated theoretically. That is the Pmax model. With the model, this blue was the tracking, and according this actual was the output which I was getting. Okay, so this Pmax, that is MPPT, that is the green one, divided by this blue one will give me my efficiency. Can you get it? So this experimentation, this was P&O with a duty cycle change in a value of 0.01 cycle. Okay, so this was the overall output we got. You can see here, first perturb and absorb with duty cycle change in the ratio of 0.1, the step of 0.1. Okay, I told you we are perturbing the system. Do you remember that? I told we'll perturb. Perturb is in what range you will change the duty cycle. Only slightly you will change, or you will change more. So you can see here, when we change more, the efficiency was less. When we change very less, your efficiency has improved. That is also clear from this. Okay. Then we just see we saw the peak overshoot is there or not, settling time, the dynamic delay, steady state error, and how many sensors are required here. Okay, so these things were noted. So here you can see we just carried out the same experimentation with incremental conductance method, then with the neural network, then adaptive neurofuzzy inference system. So if this neural network and ANFUS, what we did, we took the data from the incremental conductance method itself. That is, what is the voltage, what is the current, and what is the duty cycle. We took the data, we trained our neural network and ANFUS with the same data, and we saw the output. And ANFUS, adaptive neurofuzzy, was giving me a better result. It was giving me around 93.31%. In the sense, what is the input coming from the PV? It was transferring around 93% to the load. Okay, so this was the efficient maximum. Yeah. Set pointer, say it varies. It is not the same for every condition. It depends on the irradiation. Say when I am doing P&O, I can tell you, if doing the experimentation at perfect thing is very difficult. Is it? Say at that time I'm turning on the system. Sometimes the room light will be more. Okay. So when we did in say simulation, we had a set point of 1000 watts per meter square, or we had we set the curve. The irradiation curve, we have set it, the 1000 watts per meter squared, and that is tracking the 1000 watts per meter squared. But when you do in real time, this is not possible. Okay, so that's why what we did, we just, that's why we measured the irradiation, what is the irradiation at that instant. For different experimentation, we got different irradiation. But for that irradiation, what should be the Pmax value? With that Pmax value, how much we have got, we have found the efficiency. Okay, but we have tried our the level best to do the experimentation at the same time. The another problem what occurred is, say when we turn on the PV inside our room, the temperature of the PV goes on increasing. We do the experimentation for a long time. Our PV, say we started at 28 degrees, sometimes it will go to 34. Then what we have to do, we have to cool the PV, because then, yeah, halogen lamps are there, they heat up the panel. So we did a lot of things. Then what we did, we cooled it, we just turned off it, and we saw that at least the temperature we maintained, because irradiation we can't do anything, because irradiation is, our room light also comes into picture, and when you're turning it on, it depends on many parameters, so we can't do anything. Okay, so that's why the set parameter is nothing but here the irradiation which is acquired at that instant. Okay, so depending on that irradiation which is coming and the temperature what is acquired, what should be your Pmax? So that Pmax is our set value now. Okay, that Pmax, and what is MPPT giving me? With that MPPT and this Pmax, you can find it. And here, when you say the peak overshoot and all, we just measure with this itself. Like from here, say this is the actual system. So how much overshoot is there? So in this case, say you can see there is no overshoot. There is no overshoot. But when we did ANFIS, there was overshoot. Okay, so I have those readings also here. I removed many of the things, but in that case, if you see, there was overshoot. Here, settling time from this, say, this is the instant we have turned on, and we are just seeing how when it got settled almost to the maximum value, like the value. So from this graph itself, we have just measured all the things. That. So no, here there is no problem. If you go and give this in MATLAB itself, now their options are there in MATLAB. That itself will measure and give you. It will take the point from where the curve is starting. It will show you this is the settling time, this is the standard time. So there you have options in MATLAB also. And other thing is we have to measure by ourselves. Say usually when we do settling time, say you have a set input as you said, and my input is tracking that, I will just go and see when it is getting settled like this. Okay, so I can say this is my starting point and I have got settled here. But in this case, what we say is, say this is my starting point. Okay, and it is almost settled, like, because this method is a P&O method. Every time you will oscillate it. Okay, so I am just seeing that from this point, it is almost settled here. It is settling. It is. Yeah, it is. Yeah. Then why this changes? That is due to P&O. P&O, I told, every time you have to go and disturb the system. This is a duty cycle. Every time you disturb. So every time you disturb, say it is coming back to the original condition fast. And this, it is 0.01 second. You are just disturbing the system. Every point, the duty cycle change is 0.01 second, but otherwise also, when you're running it, the switching you're doing at 80 kilohertz. You're doing the switching at 80 kilohertz. So every 80 kilohertz, when it is turned on, there is no much difference in this. It is settling faster only. Okay. So in some system, as I told you, if it takes more time and go and settle, then you can measure that instant. Okay, so now I just showed you this one. I have just show you the real-time experimentation how we did. Okay, so first we have to turn on MATLAB. So MATLAB is getting turned on. So we are just showing you the experimentation how in MATLAB how to do it. So when in MATLAB what happens, this whole process goes on. Okay, and when I already told you, when DSpace is connected, a window will open like this, and RTI 1104 is our model. So just click on that model. Okay, so now it will take little time. One more window will open. So just click on that OK, and a command prompt will come. The sense our DSpace is connected. Okay, and for DSpace, a key is also required. you have a pen drive like thing. So you have to put on that. So here you have to just click OK. Okay, and now a command prompt will come. So then whenever you want to connect DSpace, you require a key. A pen drive is required there. So now I'm just going and choosing my program. So my program is in the P&O, like perturb and observe. So in desktop it is available. So I'm just going and choosing my program. For the center people here, we will just see it in the laboratory also. Okay. So P&O model, I'm just opening the P&O model. So once this Simulink P&O model is open, say you can see this model. This was a model which I showed you in color also. So the analog to digital converters are put here, one for voltage, and I've connected in the 5th channel. You can otherwise connect in the other channels also. Similarly, I have a mux where I'm connecting the current probe. So if you want, you can connect more number of input. I have connected in the one terminal, or just apply, okay. And here you can see the gain. I already told you, say it is 17 volts, we just take 1.7 and multiply by 10. In our case, we took only 0.17. So we multiplied twice, 100 se multiply karke, we have taken inside. You have a Butterworth filter also connected here, not to remove the noises in the thing. And you're just, this is the P&O model. This I showed you yesterday also, I think. Okay, how to write the function I told you yesterday. So this whole program, say 4 inputs are there, parameters, enable, voltage and current. And this was the P&O algorithm which was written there. Okay, this I showed you in software yesterday. So only that model should be coming there in the hardware. And now just the duty cycle, and this is the saturation. So I have just saturated the value between 0.4 and 0.95. Okay, and this PWM, so I've already told you, we are just giving the 0 to the other ports, and thus PWM is given here. And PWM, you can just see the frequency setting. While doing the experimentation, we did for 120 kilohertz also. So that was a video which we recorded. We did it with different frequencies. So this model was for 120 kilohertz ka humne jab kiya tha, that we recorded. So you can see here, whichever channel you want, first channel, second channel, which channel you want, you can just connect it. Okay, so we have just connected to the second channel. And so now we have some parameter setting. We have to go to simulation, configuration parameter, and there we will just do some setting and then flash the program. So first, solver setting, it should be 0. And whenever you run hardware, it should be infinite. It should run for infinite. Hardware, again, fixed point is required. And your time step was 0.001 step we have taken. And ordinary differential equation 3 was used for solving this. So when you choose fixed step, automatically it is ODE 3. Then this block reduction, initially it will be checked. You have to uncheck this optimization. You have to go and do that. And here RTI 1104 should be chosen. That is, you choose browse and choose your RTI 1104. Okay, RTI 1104 and click OK. Okay, so then build. So here a small error will be shown because we have masked the parameter. So TS value we have to give. When it runs, it tells me your TS value is not set. So reset it. So it's giving me an error that TS underscore control is not set. So we have masked and we have kept the time step. So that is 0.001. Again, I have to give that. And again, run the program. Just burn. Control B can also be done. Or you can go to simulation parameter and build the program. So once you build it, it is similar to your microcontroller. It will just flash the whole program inside your DSpace. Okay, so when it is flashing the whole program into DSpace, it creates a .sdf file. It creates a .sdf file. So that file is very important. That file we will be just taking in order to see the real-time parameter. I'll just show you those things. So here you just see at this point now a .sdf file will be created. See, yeah, here now see, you can see here .sdf file is created. Okay, po_test2.sdf file. So this file is very important file which we will be just taking in order to see the real-time parameters. So now the program is flashed. Now your program, what you have written was burnt into our D space. Now close everything and we will go to the D space environment in order to see the real-time parameter. So here you have the D space control desk. So this is the icon which usually the D space people will install it for you. Just double click on it. The D space environment will open. So this is the control desk and we have to just accept their terms and conditions. So first we will be doing that and then we will go into their environment. So now just drag this down. So the accept option will come and just accept it. So once you go into this environment, now that .sdf file you have to just call in this environment and you can just see the voltage, current, duty cycle, whichever parameters you want to see real time. Whenever you're varying it there, here also it will vary. And you can see the original values here. This value you have to record when you're doing the algorithm. Say now P&O is already flashed into it. Now you just turn on the light, you just take the parameters, you just record it and find the efficiency of the system. So that is what you have to do. So this process, it takes little time. So we'll just see this. So now this is the control desk environment. We have to open a new experiment. So go to new project plus experiment. I'll be just opening. So it is a project plus experiment. So this window will open and just we have to just do next and go next. So I'm just doing next. I'm doing next. I'm going next. And now here DS1104 is chosen here. Already that is the controller. It's not clear coming there. So now just choose, you have to import the .sdf file. So import. Here it is not clear for the audience, it is clear. So now I have to just choose my .sdf file, which was in the desktop created. I have just found the location, that po_test.sdf file I'm choosing. And I'm just clicking OK. Sorry, open. So that SDF file is called here. Now just finish it. Okay, just click finish. So it is creating the project and that .sdf file will open here and now I will just go and see all my parameters. So here you can see p_test.sdf is here. Click on that. Model root will be there. So in that model root again click it and just go and choose whichever parameter you want to see. You want to see current, you want to see voltage, whichever parameters you want to see. Just drag and put the plotter. You can plot the thing. Okay, so here I've seen the current. Now duty cycle I want, just drag it. If you want to see plot or display or anything, you can just see it here. You have to just drag and put it here. Again, I'm just taking whatever parameters you want to visualize, you can just drag and put into it. After putting all these parameters, say now I'm just putting power and next I'll just take the voltage. So I just want to see what is my power, what is my current, what is my voltage and duty cycle. So all these parameters I can record it. Okay, so first I have to calibrate my system. So here this green color option which you can see, just click on it. That is for start online calibration. So what will happen, the system will start calibrating. It will do it by itself. And you can see some of the parameters, say duty cycle and power is changing here. Now I'll next do measurement. So when I do start measurement, the blue color arrowhead there, click on it, it will start measuring. So this value is a real time value, which is coming from my PV panel. Okay, I can see here the voltage is 5 volts now. But this is according to the room temperature. I have not turned on my halogen lamp. According to the room condition, according to the irradiation of the room, it is 5 volts and the current is 0.002 minus may. In the sense, current is not flowing through the system. Now I've turned on my PV. So now I can see it has gone to 10 volts, 10.7 volts, and my current is 0.5, 0.05. Okay, so 0.5, I'm sorry, 0.5. In the sense, current of the PV panel also have increased, and I can see here some power. 5.2 is the power because the current is 0.5 and voltage is 10. So power is almost like V into I. So you can get 5 point something is the power tracked. So now without MPPT, I'll do it. With MPPT, I'll do it, and I can find. And the PMAX model also I am having. You can find the efficiency of the system. So I'll just show you how to record the parameters also here. Next, we will be just seeing how to record the parameters. So in this itself, we can do the experimentation with partial shading also. You just take a small cardboard and just shade some of your cells, and you can just apply algorithms like GA, PSO and all, and you can do it. Okay, so now I'm just going to show you how to record the parameters. So for recording, the red color symbol which you can see here, start all recording. So it will start recording. So now you can turn on, turn off, or whatever you want to do. You just record the parameters. So now the recording is going on. I can stop the recording after when you want to stop it. And I can take the, you go to measurement and save the buffer. So they save that value, and that is the recorded values have come here. Now I can open a new layout again, and I can see the real-time experimentation value. The recorded values are here. You can just go and see all the parameters which you want to see. Model root, voltage and current are there. So if you want to see these things what are recorded, you can just go to insert, have another layout, and just drag these parameters, and these are the recorded values. Okay, so this is at one particular instant, it is just showing me what it has recorded. Okay, so you can have a whole Excel sheet. This is only for one particular, I did it for a small time, it is coming and just showing the whole variation. Between 10 and 11, it was varying, at full value it's showing. You can even record this in the Excel sheet. That is CSV format you can save. So that I'll be just showing you. So for that, again, you go to the record, you have export. So export, you can just have .mat files, you can have SVC files, CSV files. So I'm just saving it in CSV so that I can open and show it, show the values in Excel. So now I'll just go to Excel sheet and just open and show you. So I've saved this. Now I'm just going to the Excel sheet which was created .csv. I'm just double clicking on it and I'm just opening. So all the values that with the time it will come, at what time we have recorded, what are the different values, everything with the, I have just here 4 parameters, I think, no, all the 4. So how much, whichever parameters you choose, all those parameters will come here. So it is taking little time. So here you can see the whole data. So here around 3 parameters I have recorded. So the voltage, current and power, I think. Sorry, this is voltage, current and duty cycle. Okay, so these are the values. So all from similarly the Pmax also you put here. Pmax value also will come from irradiation and temperature. So with that, the Excel sheet is there. You can find the efficiency of the system. Okay, so this is how you do it real time and find the efficiency of a system. So this we did with DSpace. Now I can just show you the same thing using Arduino. Okay, so I can just show you the Arduino kit. So I have some experimental setup videos also. I'm just leaving that. Let us now just go and see this Pmax model. I'll just show you the Pmax model which we have done in so this Pmax model which I have done, I'll just show you that model. Then after that, we will just go to the Arduino. So opening, I'll just enlarge and show you. You need not worry, it's not little, it's not clear there. The model is opening there. Pmax final. So I think all of you remember the Pmax. So this is the Pmax model. I showed you separate open circuit voltage, but when it was made, it was a big model like this. Okay. So you can see this was the model. Okay, so irradiation temperature, when you do it in real time, you'll remove this and you'll give the real time value here from any system. So this is when you double click on it, the window will open. So here you can see the overall system. Okay, open circuit, short circuit, and the fill factor. So इसमें all the blocks are very simple. You can see here it is constant blocks. This is a constant block. Just put the constant block. Addition blocks. Okay, these are the product blocks. Okay, these are input output ports there. So this input output ports there, when you create a subsystem, automatically it created all these things. Only thing many people will have confusion in this function block. Okay, so that's block I'll show you. It is an user defined block that I'll show you. So function block, when you use, say when two functions are coming, this is one value coming and this another function, this another value is coming here. So you want to multiply those two values, you put it in a function because there are a lot of values multiplying and they are coming. So where output of a mux should be this function block. So that I'll show you. For function block, you just go to this library and go to user defined function. So double click on this user defined function. Okay. So user defined function, you can see this is the function block. Okay. So just drag this and put it in your thing. So this is the same function block. Double click on it. And here, whichever parameter you give u1 plus u2 or this, here they have given some function you can see here. Okay. So like if you want to find the sign of your u1 function which is coming, sign of the value, say some 30 degrees. You want to find sine 30, you can just give sine of that u of 1. U of 1 can be. So when number of functions you want to multiply, add, you will be using this function block. Okay, this is a very useful block. Whenever you have a very big function, you want to add, subtract, division, you can just give it inside this. So this is what was done here. Use all the equation was there, that whole equation I have made it like this. Okay, so here you can see this is the function of this P max. So you just see here, can you find what is U1, U2, U3? What is U1, U2, U3? Fill factor, open circuit voltage, short circuit current. Okay, finally what I did separately. I want my U1 in this Pmax model is nothing but my fill factor, open circuit voltage, short circuit current. So U1, finally after doing all the combination, division, addition, U1 came, three inputs you can see here. This is three inputs coming. Okay, one is my open circuit voltage, short circuit current and this, that comes and gives my function. Okay, is there any doubt in this? It is very simple. You make this model, then go and implement it in hardware. This main model, this is not necessary. Simply if you want to do P&O, that you can wind up there. But this is required to find the efficiency of the system. Because anything when we find, we want to find whether my system is good or not. Is it? Which system is giving. So that this model is required. Okay. So now, is there time to show you that Adreno? I think it will take me only some 15 minutes. Or should I do it in the afternoon? I think the afternoon also I can do it. We have an expert from here only. Kuldeep will be doing the afternoon session. So now it is tea time. So let me finish the Adreno. Do you have Adreno block also? I'll just show you. So here you can see this is a Adreno board microcontroller. Okay, this is around only 400 rupees. Okay, if you want to get the full kit, okay, this I got it for some 1,500 or something. You can get it in Amazon or any robot mart. If you go, you can choose which are. So when I got it, I got motors, I got some of the sensors, I have the breadboard and all the things. So you have the LCD displays and many things, many small motors. Okay, so you have all the resistors, capacitors. So if you want, you can get the whole box, or only this you want. This is only 400 with this USB port it will come. Okay, this is 400 rupees online. This is also more than enough just if you want to connect the controller, and then you can choose which are your sensors and all. You can make your own sensors with resistors and all these things. Okay, so here this Adreno, I'll just show you the pin diagrams in PPT so that you will understand still clear. So you can see on the screen, this is the Harjot Adreno. So this is the Adreno Uno, which I showed you. Okay. So this Adreno Uno, if you see, it has 14 input-output ports. So you can see here, these are the 14 digital input-output ports. You can make these ports either input or output. And these sine waves here, these sine waves are PWM. So 3, 5, 6, 9, 10, and 11 can be programmed as PWM outputs or inputs. Okay, PWM outputs, like PWM, when you mainly want, you want to take it PWM as output only. So these pins 3, 5, 6, 9, and 11 can be made as PWM outputs. Okay, then you have here, this is the microcontroller. Atmega 328P is used as the microcontroller here, Atmel microcontroller, and this has 6 analog input output. Sorry, this is 6 analog input ports, A0 to A5, and then it has ground pins here. You can take grounds here. 5 volts you can give here 3.3 volts if you want to take as output. So these are some of the ports. And apart from that, they have 2 ports. One is a USB port where you can directly connect our system to the USB. 5 volts will be given from the USB. And another one is the 5 volts supply when you want to use it as a standalone system. Okay, when you want to use your system as a standalone system, then you can go for this one. This one can be, this port can be used. Say for example, you want to use your system as a wheelchair individually. You can't go with your computer everywhere, is it? So in that time, what you do, you just give 5 volt supply at this instant, at this port where you can see here. Separately, you can give the 5 volt supply and you attach it in your wheelchair anyway, and this whole system will start working accordingly. So you can see here, these are the different pins, as I already told you, digital input output pins. Okay, you have this Adreno Mega, and these are the different pins. So this is a very simple hardware, as I already showed it here. This is the Adreno pin with this port here. Okay, so now we have to just connect this to the USB port. So I'm just connecting this USB port here, okay, to my computer. Okay, I've just connected to my computer. Okay, and first I have to test whether this is connected properly or not. And this Adreno, if you go to the Adreno website, you can download its software. Okay, Adreno ka website mein jana hai. It is ARDUINO. Adreno, ARDUINO, Adreno. You just go to the website. You can just download the Adreno software. Okay, so this software, you have to just see that whether how many bits your computer is. It is 32-bit or 64-bit. Accordingly, you will be choosing which Adreno your software you have to download. You see whether your operating system is Linux or it is Windows. Accordingly, you will be downloading it. So now we are just going to the Adreno environment. So this is the Adreno port. Okay, this is the Adreno icon here. This is the Adreno port. Just double click on it. Okay, just double click on it. This window will open. Just I double clicked. So this window is opening here. And now what you have to do, in this window, already the program is here. You can just go and see the other programs. Go to this icon. You just click on this. You can see here, open basic programs. So digital input output program, all the programs like buttons, debounce, analog, communication, you want to connect motors, all these programs are already existing. Okay, so that is the simplicity here, and the programming is similar to C program. You can see here, say void setup, pin mode. So it's just similar to C, how we write C the same way, the programming, and there you need not learn it also, because what all possibilities are there, they have given in the examples. What you have to do, you pick, you want to connect a motor, stepper motor, go to the program there, pick and put it in your program. You want to connect an LED, go and pick and put it in your thing. So now, first to test our thing, what we are doing, we are just going to the load program. Okay, basic program I'm opening, and I'm just choosing my blink program. 1 second, I'll just let me try with this. It's not enlarging there. Okay. Anyway, I'm just going to the basic Blink program here. I'm just opening the Blink program. So this is the Blink program. Okay, I think all of you can see the program here. It is very simple. The Blink program, what I've written, void setup. In the sense, why I've given void, this system will not give me any output. It's not going to send any arguments out. So void, I've given void setup. First, this is a thing once it will run. I am setting the ports. So pin mode. So you can see here, pin P is small, but in Arduino, the every second word, there is no space, but it starts in capital. Pin mode, the 13th pin, I am just putting as my output pin. Okay, I have 0 to 14 pins there. I showed you. In that 3, 5, 7, all these things are PWM. So you can choose any pin you want. I am choosing my 13 pin as output pin. Then void loop. Void loop में मैंने क्या किया है? I have written digitally write the 13 pin as high. I am digitally writing this. Again, this is the main loop which will run continuously. This is the loop which runs continuously. So I am writing digital write 13 pin high for 1 second. Okay, this is wait for a second. Delay of 1000, I've given 1 second. Then again, I've made it low for 1 second. So now again, you will get pulse as output. Okay, high, 0. So this is again a PWM output only with a fixed duty cycle. If you want to vary the duty cycle, you can change your program. So let us see this program. The procedure to do this is very simple. You can see here, and you can see a icon here, this one. I'll be just clicking on this, the program will load. Okay, so this is very simple. It will be flashed into my system. Before that, you have to see some test setting. One is this tools. Go to this tools and go and see this board. So which board is connected? So in case first time when you're connecting, it will be some other board. If you want, you Arduino, click on that board. Next thing, the port to which it is connected. So you can see it is connected to COM port 3. In yours computer, it may be some other COM port. Sometimes 4, 5, 6. I have seen when we do it in the lab, around 5 COM ports will be coming. So you have to choose in which COM port your Arduino is connected. How will you identify that? You have to go to device manager. Device manager में आप चले गए, any system, say you have connected a printer, you want to know which COM port it is connected, you can go here. Go to this option. You have ports, COM port option here, is it? Just click on that. You can see only Arduino is the only external device connected here. And to which COM port it is connected? COM port 3. So if you have any doubt, say in your house, it maybe printer is connected, you have connected number of other accessories, then you have to go and see which COM port your Arduino is connected. Okay. One more thing is, sometimes I'll just show you with Simulink when you're doing it. So this COM port, you have to know at what baud rate is set here. Say you have different baud rates. So 9600 is the baud rate set. When you do the programming, I'll just again remind you this, 9600. Okay. So with this is how you just, 2 things you have to do. Go to the tools and see whether your board is Arduino Uno and which COM port you are connecting the thing. Okay, now it's clear. Now what we are doing, to the 13th pin, just because of the to the 13th pin, I'm just going to connect my LED. So I'm just taking the LED. Once again, I'm just searching for my LED. I couldn't find it. So here it is. Okay. I think this is a working LED. So what I have to do, I have to, the LED you all know, the longer one is the anode, shorter one is the cathode. So I'm just connecting the ground to the shorter and the 13th pin I'm just connecting. It is working LED, that's why it's running. Okay. Now what I'm going to do, I'm just going to flash my program into it. So my screen, laptop screen, please. So here I just, what I have to do, this is my upload option. I think all of you can see this. I'm just clicking on this. So here, compiling sketch, the process has started. Now please the screen. So now you can see, no, serial port is already used. 1 second, there is some problem. I'll just once again, because it is in use now, I'm just once again turning on. I'm just opening the Blink program and uploading it. Should open. So it is uploading. So you can see that blinking. Once it is now, it is uploaded. So you can see the screen, done uploading option is coming. Okay, I just uploaded and you can see here, done uploading. Okay, done uploading. It is coming, done uploading. बहुत simple hai. Just click on that. The program will be uploaded and you can see this LED glowing like this. If I want to change the timing, you just the 1000. If I go and change automatically, the blinking speed will change here. So once again, if you want to see that, let me upload again and show you. So here, let me say high will be for the small time. Let me keep it as some 500. A small time, and low for a long time. Let it be like this. So I'm just doing the uploading. So now it is uploading, that is blinking, in the sense it is uploaded. Now we can just show the screen. So now we can see only for a short duration it is on, off for a long duration. Can you see the blinking changing? I can just connect another color. Okay, so in the sense, very simple procedure. Just install the Arduino and